All right, guys, welcome to lesson 21. In this lesson, we're going to talk about exponential functions. The first thing you should know is that this is the form that they take. We have a to the x, where x is the variable that you plug in, a is the base, and then it has the graph has all these different characteristics to it. And we'll look at a graph in just a second. But here, if you add or subtract, then you're going up or down. See, so it's similar to all the other transformations we've talked about. If it's outside the function, then it's up or down. If it's inside the function, like x plus c, x minus c right here, then it's inside the function and it's moving left or right. If you get the negative out front, it's reflect over the x-axis. If the negative's in the exponent, it reflect over the y. And if the c is out front, then it's a vertical stretch or shrink, depending on how big or small it is. If it's inside the function with x, then it's a horizontal stretch or shrink, depending on the size of the number, whether it's greater than 1 or less than 1. And the rules for vertical and horizontal stretching are directly opposite to one another. Okay, so what we're going to do here on number 1, the parent graph, the original graph, is f of x equals 3 to the x. All right, so I want to know what is going on at each of these. So for number 1, we got f of x to the negative 3x. For number 2, we got 3 to the x minus 2. And for 3, we got 3 to the x plus 2 minus 2. So I'm going to switch over to Desmos real quick. So if you ever, you're not allowed to use graphing calculators in this class, but Desmos.com is a free graphing calculator that you can use to kind of help you out from time to time for stuff like this. So we are going to look. All right, so here's Desmos. All right, Desmos.com is a website, but here we go. So f of x to 3x is my original, so this is it in red. And this number 1 here, as you can see, the negative flips it over the x-axis, so that's what's going on. All right, number 2, all right, the x minus 2, the minus 2 is inside with the x, so it is shifting it. So it is shifting it right 2 units. So as you can see, it moved to 2 places to the right. All right, and then number 3, it moved it left 2 and down 2, as you can see there. All right, so let's take another look at number 1. It reflected over the x-axis, so the domain is all real numbers, but the range, it tops out at 0 and it goes down from there. Okay, so let's go back to our notes. All right, number 1, we're reflecting over the x-axis. And my domain is negative infinity to infinity. My range is negative infinity to 0. Remember, you list it from low to high, and you list it from low to high, and the range tops out at 0. So 0 is on the high end. All right, let's go back. So number 2. All right, we have it moved it right 2. So the domain in the range of the original never changes. So it's going to be right 2. And my domain is all real numbers. My range is 0 to infinity. All right, and again, I'm pulling this from up here. So, all right, and then here I'm going left 2 and down 2. And we can go back to the graph and check, but you can kind of get the idea here, based off the first 2, that the domain is not going to change. Will it ever change? Maybe. But the range is what is most susceptible to all these different changes that we're making. So the original range is 0 to infinity, and if I move it down 2, now my lowest point is negative 2. So this would be negative 2 to infinity. Okay? So that's what we got. All right. The thing that you use the most with the exponentials is exponential function and word problems and application problems and stuff like that. So we have a natural base exponential function called e to the x, where e is a irrational number similar to pi, and it's approximate, where pi is 3.1415 and so on and so forth. E is 2.71828 and so on and so forth. All right, so number 4 says the exponential function models the gray wolf population of the western Great Lakes, f of x, where x is years after 1978. Project the gray wolf population in recovery area in 2014. Okay, so if x is the years after 1978, we need to figure out how many years 2014 is from 1978. Okay, so 2014 minus 1978, that's going to give us 36, and that's what our x is going to be. So f of 36 equals 1144 e 0.0325 times 36. You plug that into your calculator and you crunch your numbers and you get approximately 3686 wolves. Okay, so approximately 3,686 wolves after 36 years. All right, compound interest. All right, so compound interest is a beautiful thing if it's working for you. It's a terrible thing if it's working against you. So if you are investing your money in retirement or different accounts, you want that interest to be as high as possible. But if you're buying a house, buying a car, taking out loans, you want that interest rate to be as low as possible. Okay, so there's two different ways you can think about compounding interest. First of all, is it compounding over the year at different intervals? It could be annually, it could be semi-annually, monthly, daily, all the things. Or you can compound continuously, and when you do continuously, you throw the e in there, and it cleans up the formula a little bit. So we're going to take a look at some of these problems and see what we got. So on number 5, it says, suppose $1,000 is deposited in an account paying 4% per year, compounded quarterly. Okay, well, using my formula above, A is the amount of interest, and P is your principal. So I'm depositing $1,000. All right, 1 plus R. R is my percentage rate, but you got to write it as a decimal. So you got 0.04. It's compounding quarterly. So I divide N is the number of times per year it's compounding. Quarterly would be 4. And then you raise that to 4 times the number of years. So it says after 10 years. All right. So if it's 4 times a year for 10 years, it's 40 times it's going to compound. So you set up your equation, and then you crunch your numbers. And that's going to give you 1,488.86. We're dealing with money, so we'll round to 2 decimal places. All right. 1,488.86. So if you don't touch your money at a 4% interest rate and it's compounded quarterly, after 10 years, you're going to gain almost $500 on top of that. Is that the best? No. But typical annual inflation runs somewhere between 3 and 4% on average. At least that's what it was when I was growing up. It may be different now. But if that's still the case, then 4% is just barely keeping up with interest. So your money is not worth any less than it was the day you put it into it, but it's also not really worth any more. So how much interest have you earned over that? So you just simply subtract your previous answer minus 1,000. And you get 488.86. All right. Present value. Brendan must pay a lump sum of $15,000 in 8 years. What amount deposited today, present value, at 2.4% interest, compounded annually, will give $15,000 in 8 years? Well, so in this case, we know our formula, but the only thing we don't know is our principal. We put in today. We know that he wants $15,000. P, and then we're going to do 1 plus 0.024 over 1, because it's compounded annually, and then 1 times 8 years. All right, so we're going to crunch these numbers. And the inside is going to simplify. So we got 15,000 equals P times 1 plus 0, or 1.0224 to the 8th power. All right, then you would divide, so P equals 15,000 over 1.024 to the 8th power. You put that in your calculator, and you would get approximately 12,407.71. Okay, so 2.4% is not a lot. If you got some time to wait, it'll get you there, but it's not great. All right, if only $12,025 is available to deposit now, what annual interest rate is necessary for you to increase to $15,000 in 8 years? So we're going to do the same problem, but this time we don't know the interest rate. Okay, so we got 15,000 equals 12,025 times 1 plus R over, still compounded the same, so over 1 and 1 times 8. All right, so let's clean this up. First thing we can do is divide the 12,025, and so that's going to give us 15,000. We're just going to write it as a fraction. We're not going to do anything with it. We're not going to simplify or anything like that at the moment. Your calculator is going to do all the heavy lifting. So this is going to be 1 plus R to the 8th. All right, so we have an exponent. We need to get it out of the exponent. So we're going to take the 8th root of everything. And so when we do that, that's going to give us 1.028088125 equals 1 plus R. And you subtract the 1, and so you get R equals 0.028 08125. All right, but our rate is usually given in percentage, so we do the R is approximately 2.8% or 2.81% when you round. So that's how you do that one. All right, so for number 7, suppose $8,000 is deposited in an account paying 5% interest compounded continuously for 6 years. Find the total amount on deposit at the end of 6 years. All right, so we're looking for A, but now we're using that second formula, the A equals PERT. So we're depositing $8,000. E is just E. All right, rate is 5%, so we got 0.05 times 6. We punch that into our calculator, and that's going to give us $10,000, 798.87. Okay, 10,798.87. So not terrible for 6 years. It's definitely better than the previous problem where we did 2.4% over 8 years, and it barely made a dent. Okay. In problem 8, we found that $1,000, and actually this is problem 5. In problem 5, we found that $1,000 invested at 4% compounded quarterly for 10 years grew to $1,488.86. All right, compare this. All right, so if I had done annually, I got $1,480. If I had done semi-annually, I got $1,485. We did quarterly, but you can see as you go down, the more you compound, the more money you get. And okay, so number 8 is not really a problem so much as it is just kind of an explanation of what's going on. The more often you compound, the more money you get over time. So that means two things. One, you want it to compound as many times in a year as possible. Also, the beauty of compound interest is the earlier you start, the better off you are. So let me give you an example, and I'm not trying to be political, but it's just the reality here. All right, so if you know Dave Ramsey, he talks about how the same person if you start putting money into an account, earning a certain percentage every year, $2,000 a month from the age of 19 to 25, and then you just stop. A second person will start putting $2,000 a month in, and they will never stop, starting at age 25, going to like 65, and they will never catch the person that started at 19 who stopped at age 25. Right? The faster you start putting money away and letting compound interest work for you, the better off you'll be. Which is one of the great things about the Trump accounts that just went live and on July 4th, 2026, is that they started giving newborns $1,000 in account from birth. All right, so they get potentially a 20-year head start of everybody else who could potentially put money into an account, and you can add to it over time. So again, the faster you can start, the better off you'll be. So again, not trying to be political, but that's something to think about. And so if you have kids or are planning on having kids, having them, whether you use Trump accounts or not, having money set aside for them and let it grow over time from the day they're born, all right, you can't beat that. All right, so that's it for this lesson. I'll see you in the next one.